Hello everyone. Today we are going to discuss various operators used in Verilog with some suitable examples. So expression is a combination of operands and operators that produce a results based on the value of operands. So expression is a combination of both operands and operators. Let us consider. Now if you see, if I write A is equal to B plus C. Let's consider A equal to B plus C, where here this B and C are operands. This plus is here, that is a operator, where we can call this A as a result. So now here it produces a result based on the value of these operands. Now this is a simple expression like A equal to B plus C. For example, if I write, see another example, if I write like this, A is equal to B ampersand and C, or we can write, okay, A is equal ampersand B, or maybe you can write A, B ampersand C. So these are the three different expressions but use a single operators. So that same symbol having different meaning. So where we use this operator. So in this case, so it is a logical operator. You can say logical AND operator. So we need two operands, a binary operand, because we required two operands B and C. This is the logical AND operators. So it is a unary reduction operator. The two reduction AND operator. This one is the ampersand B. So it is a unary operator because we have only one operand. So now in this expression, this ampersand is as a unary reduction AND operator. So whereas this B and C, this is a bitwise AND operator. Bitwise operator. So now the meaning of this operator is varied where we use this operator in the expression. So we will discuss in detail about these operators, okay, in this video. So expression is a combination of operands, and operator that will produce the results based on the values of that operands. In Verilog, we have various operators like arithmetic, relational, equality, logical, bitwise, reduction, shift, conditional, and concatenation operators. So what will be the operands in this expression? That operand may be a constant number, including real or maybe string. That may be a parameter or maybe including a local parameter or specified parameters. It may be net, reg, integer or time variable or bit select or portion of that maybe we can call part select. That may be real or real time variable or any array element or maybe a like a one bit or like a bit select of that array or maybe portion of that array. A call to a user defined function or a system defined function that retain any of the above value. So these are the various operands we use in the expressions. So coming to the arithmetic operators. So these are the various arithmetic operator: a plus b, a minus b, a multiplied b or a times b, a divided by b, a modulo b, a to the power of b, and these are unary plus a, unary minus. Default all operands are binary operands. So here we have two operands, whereas this is the unary operand, we have only one operand. So now we'll discuss initial. See this example. So assume that a is equal to 9 and b equal to 4. A plus b is 13. A minus b equal to 5. A into b is 36. A divided by b. Here we are getting quotient. 4 to the 8, we are getting quotient 2. So a modulo b, here we are getting the remainder. Where this is a unary, minus a means minus 9. So how do I represent minus 9 in the 2's complement? Let us see. Yeah, for example, we'll take this is a plus 9. So how do I represent plus 9? So 1 0 0 1. No, 1 2 4 8. This is the plus 9. So to represent minus 9, just you need to convert into 2's complement form. Already we discussed in the previous class how to represent, okay, a 2's complement of a given binary number directly. Till first one, write as it is. complement remaining all. Okay, 1 1 0 1. Now this is the minus 9. Now see, this is the minus 9. So we are getting here. So now this is the minus 9 1 0 triple 1. So in binary, what is the value here? 23 we are getting. Clear? So for the division or modulus operator, if the second operand is 0, then the entire result will be x. Clear? So now in arithmetic operators, so second operator is 0, then the entire result will be x. So it is infinite, we cannot represent that. So that is unknown, we can represent as a x. The presence of z or x in a range or wire being used in an arithmetic expression, if one of the operand in arithmetic expression is x or z, the result in whole expression being unknown. If one operand in the arithmetic expression is x or z, the result shall be unknown. And the result of a modulus operation shall take the sign of the first operand. So now in case of modulus operation, the result of that sign, okay, will take as a first operand sign. So if either operand of the power operator is real, if any one of operand in the power operator is real, then the result type shall be a real. Now see, these are the various operators. Now see, for example, so knowing that operator and also now like finding the result of that expression doesn't matter here. So in any programming language, you should know when to use these operators and how to use these operators. That's a very important. So without knowing, if you know that, okay, I can find the expression result of the given expression, is doesn't matter. It won't fetch much. So you should know so when to use these operators and where to use also. Now for example, if I see arrange 3 down to 0 a b c, here I declare a b c as a 4-bit vector. Now I can write a plus a equal to b plus c. It is a valid expression. Now if you consider like integer a 3 down to 0, integer b 3 down to 0, integer c 3 down to 0, it is an array, it is not a vector. We cannot perform arithmetic operation on directly like this, a equal to b plus c. It is not valid where this b and c are arrays. So it is valid now. We can take a singular value like a single bit a of 0 equal to b of 0 plus c of 0. That means you should know where to use these operators and when to use. It's also very important. Now see in this case, now for example, integer a comma b, integer real c. So now if you consider if a equal 100, b equal to 3, c equal 3.0, so the result a by b is 33 because it is an integer division. Both a and b are the integers. So whenever if I declare this c as a real, now see result a equal a by c. What is that now? Here this is a real division. The resultant also, the result also in the real form, right? So based on the operator type, so here both are integer, it is integer division. Is one operand is real, then it is a real division. So you should know where to use, how to use these operands effectively, right? Now these are the various okay modulus and power operators. So just for understanding, I gave this slide. Just pause the video and try to find the expression, okay, find the result of these expressions, and just by observing, by finding the result for this expression, you will get an idea, okay, so how can you use like modulus and power operator effectively. Please pause the video and check the result of a given expression. Now the next operator is the logical operators. So now a and b, so evaluates true if a and b are true, a or b, so evaluates true if a or b are true. This and logical and, this is a logical or, this is a not logical negation. Convert non-zero value to 0 and vice versa. Now see, the result of the evolution of logical comparison shall be 1, we can define as a true, or 0, we can define as a false, or maybe if the result is ambiguous, then we known as a x. So the result of any logical operator should be either 0, 1 or x. The precedence of and, logical and, is greater than logical or. So in operator you should know the precedent of operator also, because if single expression contains multiple operator, you should know the precedence, then only you'll get a correct result. So now the precedence of logical and is greater than logical or, and both are lower than the relational and equality operator. We will discuss these relational and equality operator later in this video. So the logical operator precedent is lower than relational and equality operators. So unary logical negation operator convert a non-zero or true operand into 0 and a 0 or false operand into 1. Anything other than 0 as a true. Even it is a negative number, it is a true only. Now see, we'll see some examples here. Logical AND. So if you see 1 tick be 1 and 1 tick be 1. So already I discussed in the previous video how to represent and numbers are constant in Verilog. Okay, that to sized or unsized and also signed or unsigned numbers. If not, please visit that video, and there I explain how to represent a constant or numbers in Verilog. So now here 1 tick be 1 and 1 tick be 1. Both are true, then output is true. So 1 tick be 1 and 1 tick be 0. 1 and 0. True and false. So in logical AND we'll get a false. So one operand is 1, another operand is x. If any operand is x, now here x, 1 into x, that based on this operand the result will be finalized. If it is 0, the output is 0. If it is 1, 1 and 1 will get 1. So the result is unknown, ambiguous. So we get as result as we represent x. So 10 and 12 both are non-zero, both are true, so result is 1. So 10 and 0, one operand is 0 in logical AND, then the result is false, represented as a 0. So here 100x and all zeros. So one operand is 0 irrespective of other operand. It may contain x, z or anything. If one operand is 0 in logical AND, then the result is 0 only. So now here 100x and 0001. So the result is 1. You may get a doubt. So the operand contain x. So how can we say that it is a true? So now if we say 100x, what are the possible values here? We may get 1000. X may be 0 or x may be 1. So in that case 1000, one case, that is a true only. Another case, maybe x is 1, 1001. That also considered as a true. So irrespective of x, this operand is true. True into true, like here, like both are true, the output is true. Clear? So same way we see logical OR. 1 or 0, 1, 0 or 0, 0, 0 x. The result depends upon this x. If we consider x is 0, the result is 0. If x is 1, the result is 1. So the result depends upon this operand. The result is unknown, ambiguous. So we can say it represented as a x. So 10 and 12 both are true. Other than zeros we consider as a true. So true are true, then 1. Here 1001 and 000x. Now we may ask here. So here one operand is 1, another operand is x. Irrespective of other operand, if one input of this logical OR is 1, then output is 1. So now here that result is 1. Here 000. So this is a 0 and 000x. So now if x is 0, then output is 0. If x is 1, the output is 1. So that result of this expression depends upon the x in this operand. So in that case, the output is x only. See, but here in this case, now one operand is 1. Irrespective of other operand, the output is 1. Now same way, logical negation. It convert non-zero to 0, 0 to non-zero. So 1 tick be 1, 1 as a 0, 0 as a 1, 5 is a non-zero, consider as a true, the output is 0. Same way here, a 4 tick be all zeros. It is a 0, so we will get logical negation means 1. So by this example, I hope you understand. Okay, so what are the various logical operators are there? Okay, how can we find the result of a expression contain logical operators? So coming to the equality operators, these are the 4 equality operators we use. A equal B, A equal to B. So here we have 2 type of equality operators are there. One is the logical equality, another one is the case equality. So this is a case equality. So here 3 equal operators are used. Now in this expression, we including x and z also. While comparing in this, okay, so we consider x and z also. So A not equal to B. We are considering x and z also. Clear? Whereas now the output of these 2 expressions, either 0 or 1, not x. I will explain in detail with some examples. So A equal to B, A equal to B, result can be unknown. Here we'll compare A not equal to B. A not equal to B, result can be unknown. Maybe either maybe 0, 1 or unknown. But in this case, either the output is 0 or 1. We'll see. So in relational operator, produce the result shall be 0 if comparison fails or 1 if it is succeed. If comparison fails, okay, the output is 0. If it succeeds, the output is 1. So for the case equality and case inequality operators, so this one is a case equality, this one is a case inequality. Okay, in this case equality and case inequality operators, the comparison includes x and z bits. So we compare whether it is matches with x and z also. So the result will be always 1 or 0. The result is not unknown in case of case equality and case inequality operators. So these two are the logical equality and logic inequality operator, equal, equal and not equal. If the operands have unknown or high impedance bit, the result is 1 bit value, that is unknown x only. In case of logical equality, logical inequality, if one operand is unknown, either maybe x or maybe z, okay, so the result is unknown x only. Now see this some example here. Logical equal operator, logical equality operator. Here 4 tick b 1010 equal 4 tick b 1010. It is a logical equality. So here we are comparing first bit 1 1, second bit 0 0, that bit 1 1, yes or no, 0 0. So everything, all 4 bits are matches, the output is 1 here. Now you see in this example, so first bit is 0, first bit is 1. Okay, there is, so if it is 0, here 1 not matching, both are not equal, the output is 0. Now see here 1 0 1 0, here 1 0 x. One operand contain x or z. In case of logical equality or inequality operator, the result is x. Here one other operand, in this fourth example, one operand contains z, so output is x. Irrespective of other operand, if one operand contain x or z, then the result is x only, unknown. So whereas in case equality operators, so now here in this case equality operator, we are comparing x and z also, we are including x and z also. Now here 1 0 1 0, here 1 0 1 0, it is matching, the output is 1. Clear? 1 0 1 0, here 1 0 1 1, it's not equal, so the output is 0. Now here 10 x 0, here 10 x 0. So we are comparing 0, first bit, second bit x, and here also x, that bit is 0 0, and fourth bit 1 and 1. So all 10 x 0 matches exactly with 10 x 0 in other operand, so the result is 1. Whereas here 10 1 0, here 1 z 1 0, here see this is the 0, here this is the x, not equal, so the output is 0. Now in case of 10 xz, so 10 xz, both are same. So it comparing both x and z also, it include x and z also in the comparison. So the output is 1. So from this you observe that the output of logical operator is either maybe 0, 1 or unknown. Whereas the output of case equality or inequality operator, it should be either 0 or 1 only, not unknown. I hope you understand. Clear? So now coming to the relational operator. So we have 4 relational operator: a less than b, a greater than b, a less than or equal to b, and a greater than or equal to b. So now when using this relational operator, the result will be 0 if the relation is false, and if it is true, then result is 1. So if either operand is unknown or high impedance, the result will be 1 bit unknown value. If one of the operand is either x or z, then the result is x. Now all the relation operators shall have the same precedence. Okay, all the relation operators have the same precedence. So relational operators shall be a lower precedent than arithmetic operators. You should know these precedence of operators. While so if that same expression contain multiple operators, you should know the precedent. According to that, you should find the result of that expression. Now see this example: 5 less than 10 equal to 1. So 5 greater than 10, this is the false, so 0. 5 greater than or equal to 5, it is the true, we'll get 1. 1 tick b x less than or equal to 1 tick b x, yes, it's true, less than or equal, okay, x. 1 tick p z less than or equal to 10. So now see here z or x. Now see, if one operand contains x or z, the result will be x. In this case x, okay, and another operand x. One operand is x means the output is x. Here one operand is z means the output is x. Okay, it won't compare, right? If one operand x or z, directly the result will be unknown only. Now see this expression. So a less than b minus 1. So this expression is same as a less than b minus 1, because the relational operator shall have same precedent and also lower precedent than the arithmetic operators. First, even though without using these braces, it evaluate first this arithmetic operator b minus 1. After that, the result is compared with the a. But in this case, b minus 1 less than a. Okay, this is same. This is not same as a b minus 1 less than a. So if you use braces, it find the expression first, this 1 less than a. After that, b minus that result. But here not like that. If we miss this output of this expression and this expression is different completely. Clear? Now coming to the reduction operators, these are the reduction operator, reduction and, reduction or, reduction and, reduction nor, XOR and XNOR. These are the corresponding symbols. So these are the unary reduction operators. So reduction operators operate on all bits of an operand vector and return a single bit value. These are all unary operand. So in this expression we have only one operand. Okay, it operate on all the bits. So we'll discuss now how. So these are the unary form of bitwise operators. So reduction operator work bit by bit from right to left. Now see, for example, so this is my operand. If I use like ampersand this operand, so now how I, right to left, bit by bit, right to left. So 0 into 0, like 0 and 0, 0. So if one input is 0, the output is 0. Like for example, NAND. So R, all bits are 0, the output is 0. Clear? For example, if you take this R, if one bit is 1, if one bit in this operand is 1, then R output is 1. Now like that. So now this reduction operator, unary reduction operator, works on bit by bit of this operand from right to left. Like see all these examples, pause the video and try to find the result of all these reduction operator on these operands. I hope you clear these reduction operators. So coming to the bitwise operators. So these are the various bitwise operators: bitwise not, bitwise and, bitwise or, bitwise XOR and bitwise XNOR. These are corresponding symbols, right? So now you should know. So whereas the logical operator we use double and, okay, whereas in the bitwise we'll use a single and. Remember that. Now, so if single and, single operand, there's a unary and operator, unary reduction and operator. Okay, if you use a two operands in between that, if you use and, there is a binary bitwise operand. So double and between the two operand, that is a logical operator. So the meaning of the symbol is varied based on the where we use in the expression, whether single operand, double operand, okay, or maybe unary. Like, clear? Right. Now see, bitwise operators perform bit by bit operation on one operand and corresponding bit in another operand. So it perform bit by bit operation. So one bit in one operand, corresponding bit in another operand. Clear? So now, so if one operand is shorter than other, shorter operand will be bit extended MSB with zeros to match the length. For example, I want to perform a bitwise operation of two operands, like either maybe or and. For example, one operand is 4 bit, another operand is 3 bits. So while performing, okay, so this bitwise operation, so both operands should be the same size because we are performing bit by bit. Clear? So now, for example, if you see here, like so for example, one operand is like 1010, another operand is 010. So here are only 3 bits. So before performing this bitwise operand, so you should extend this MSB with a 0. Clear? To match the length. After that only you need to perform the bitwise operators. Clear? Right. So now the Z is treated as X in the bitwise operators. So this Z treated as X in the bitwise operation. So these are the various bitwise operators. Like, please pause the video and try to find the result. Now, for example, 0 and 0, 0. If anything, right? So and with a 0 is 0 only. Okay, 0 and 0, 0 and 1, 0x. Okay, 0 and Z, everything will be 0. If one operand is 0 in the AND operation, the output is 0. Now here 1 and 0, 0, 1 and 1 x. So one operand is x or z in the bitwise operator. The result is x only, irrespective of other. Clear? So see, one operand is x. So now even in AND operation, one input is 0. One operand is 0, the result is 0. Default, we know that. Okay, other than 0, for example, another operand may be 1, x or z, the output is x. Same way, now see in this bitwise OR, so one input is 1. Okay, one operand is 1. Irrespective of other operand, the output is, the result is 1 only. Other than 1 in the OR, if you get x or z, the output is x only. So better you pause this video and try to find the result of various bitwise operators here. Clear? I hope you clear this bitwise operator. We'll see some examples. Okay, right now see, let us consider here x is a 4 tick b, 4 bit, okay, 1010. Here this y also 4 bit, 1101, z also 4 bit, 10x. Now see negation x. So what is the result here? Negation x means now this x 0 become 1, this 1 becomes 0, this 0 become 1, 1 becomes 0. This is the result. 4 tick b 0 1 0. Now x and y. So we need to perform AND between these two. So we perform bit by bit. So what is the first bit is 0. Here first bit is 1. 0 and 1 0 only. 0 and 0 0 only. 0 and 1 0 only. 1 and 1 1. So now the result is 1 0 0 0. Same way x or y. So if one input is 1, one operand is 1, okay, the result is 1 only. So now here 1 1, output is 1, okay, 0 1, output is 1, clear, 1 0, output is 1, here 0 1, output is 1. So the result is 4 tick b 1 1. Like same way XOR XNOR, see XOR here 1 1, both 0 0 and 1 1. If both are same, then output is 0. Here 0 1, the output is 1. Okay, 1 0, output is 1. 0 1 1. In XOR, if both inputs are same, 0 0, output is 0. 1 1, output is 0. If different inputs 0 1 1 0, we are getting 1. Clear? Same way XNOR. So X and Z here. Now see Z. See, it bitwise operator perform bit by bit. Clear? Now if you consider X and Z. So 1 1. Okay, 1 and 1 1. 0 and 0 0. Where 1 and X. So one operand is X. Okay, the two AND operator. So now it is 0. So 0 and X is X only. Clear? So 0 and 1 0. So this is a simple example of bitwise operators. So logical operator always result a logical value 0 1 X, whereas a bitwise operator yield a bit by bit value. For example, in a logical operator, it may be 4-bit operands. The output is either 0, 1 or X. So whereas in the bitwise, for example, a 4-bit operand, the output, the result also 4-bit. It compare 1 bit in one operand and corresponding bit in another operand. So logical operators perform logical operation, not bit by bit operation. You should remember that. Okay. So logical operator gives only either 0, 1 or X, whereas the bitwise operator produces a like 4-bit operands, then output also, result also 4 bits. Clear? So here a single AND, whereas there is double AND. Remember like that. Okay. Now see this example. So X is equal 4 tick B 1 0 1 0. Y is equal 4 tick B all zeros. Now if you perform bitwise operation, so X or Y. So perform bit by bit. Okay, 1 or 0 1. Okay, 0 or 0. Okay, 0 1 or 0 0 0 or 0 0. So same way, if you perform a logical operation on these two, okay, that result is okay X 1 0 is a non-zero, that is a true, or Y is a 0. Okay, logical 1 and logical 0, 1 true or 0, the result is 1. Here 1 bit, here 4 bit. Clear? I hope you clear this bitwise operators. Okay. Then coming to the shift operators. So shift operators are used to shift the bits of a vector or group of bits from left or right. So we have two type of shift operators. One is the logical shift operator. Another one is the arithmetic shift operator. So logical shift operators are use the symbol 2 less than here, less than or greater than, whereas the arithmetic shift operators use 3 less than or greater than symbols, like less than or maybe greater than. Clear? When bits are shifted, the vacant bit positions are filled with the zeros. Now see, whereas in arithmetic right shift operation, okay, fills empty bits with the zeros for unsigned results, with a signed bit for signed results. Clear? So after shifting right, if it is in case of arithmetic operation, that empty bit, the empty position is filled with the signed bit only. If it is unsigned, with a 0 we need to fill. If it is signed number, the MSB bit is the 1. We should extend that signed bit in case of arithmetic right shift. These are the various shift operator: logical shift, logical right shift, arithmetic left shift, arithmetic right shift. Coming to this example, right? So now take one variable x is equal to 4 tick b 1100. So 4 bit variable. So if I perform x greater than 1, what is this? The right shift by how many position? One position. Now just I'll extend. Now see, just I'll see. I'll give. So in this case, now this. So in this case, how do we get? So that 1100 shifted to 1 bit right? So now we can write 110. So this empty bit is filled with the 0 only. So the result is 0110. So we are ignoring this. So empty position is filled with the zeros. Now in this case, see, x less than 2. This is a left shift operation by 1 bit. So we are shifting left by 1. So we are neglecting this one. So 100, that we are filled that empty position with the 0. Okay, shift left 1 bit and 0 filled with the LSB position here. In case of left shift, the 0 is filled in LSB position. In case of right, the MSB filled with the 0 or 1 if it is unsigned number with a 0, if it is signed number with a signed bit. Clear? So now y equal to x less than 2. Okay, this is a left shift. By how many position? We need to shift 2 position. Here it indicate 1 position, here also 1 position, here 2 position. So now this 1100 shifted left by a 2 position. Just we are neglecting these ones. Okay, so now we are appending another 2 zeros there. This is the shift left by 2 bits. Now see in this example, so a equal to 4 tick b 1010. Assume that it is a signed number, right? So the 2's complement representation of this minus 6, right? Now see, 6, this is a minus 6. So b equal to a greater than 1. That means this is a right shift, the two arithmetic right shift. So in this case, so now what is the MSB bit? What is the MSB bit here? So in case here, what is the MSB bit? MSB bit is the 1. So after shifting, we extend this MSB bit, sign bit. So after shifting, so 101, we are neglecting anyways this 0. Okay. So after shifting right by 1 bit, we are getting 101. This empty bit position is filled with the sign bit of this sign number. So what is the sign bit here? So 1. So we are extending this one. For example, if I perform another shift, what is the answer here? Like we'll get 0, 1, 1. So then we'll fill with the 1 only because the sign bit is 1. So in case of arithmetic right shift operation, so the fills empty bits with signed bit only. Okay, if it is 0 for unsigned, 1 for like signed. I hope you clear these shift operators. So now coming to the conditional ternary operators. So it's a very interesting operators. Most of the time we'll use this ternary operators. So this is the syntax for conditional operator. So conditional expression, question mark, true expression and false expression. Now this is a syntax. This is an expression, conditional expression. If this expression is true, then we'll execute this expression. If this expression is false, then we'll execute this false expression. Now see, so how we use this conditional operator, okay, to construct this 2:1 mux. This is some example I'll explain. So this is a simple mux 2:1. So based on the selection line, that output may be equal to I0 or maybe I1. Now see, so now this is a simple Verilog program in data flow modeling for 2:1 mux. Now just concentrate here. So now here out equal to based on the selection. If selection is 1, then out is connected to I1. So the if selection is this is 1, okay, if it is true, then out equal to I1. If it is false, if cell is 0, then out is I0. So now we can use this conditional operator effectively, okay, like to build this mux. I think we know this, like NAND and NOR are the universal gate. We can design any gate by using this universal gate. Same way this mux also universal element. If you want to develop any expression, we can use mux. Clear? If the conditional expression result is ambiguous, for example, this conditional expression is ambiguous, unknown value. So in that case, what we do, we both true and false expressions are evaluated, the results are then compared by bit if bits are different. Now we compare these two expression. Whenever the conditional expression is unambiguous, like ambiguous x, okay, so we evaluate these two expressions, we compare bit by bit. If both bits are same, we return that as the output. If the bits are different, that return as the x value. Now we'll see some example, right? I'll explain, right? So now conditional operators can be nested. Each true expression or false expression can itself be a conditional operator. So now here in the true expression we can write another conditional operator, ternary operators. So in false also we can write. So we may get a doubt. Okay, the same logic we can implement by using if else also. So why we need these conditional operators? So now so we cannot use this if else in like a continuous assignment like this. Okay, so we cannot use this if else statements in a continuous assignment like this in data flow modeling. Okay, in Verilog, particular to in Verilog, so we use this if else only in the procedural block as a procedural statement in the always and initial. We never use in the continuous assignment like in assign statement. But this conditional operator can be used either in continuous assignment or maybe in the procedural assignment. And also we can use this conditional operator in the display statement also, dollar display. We cannot use if else in the dollar display statement in the system task. Okay, we can use this conditional operator in the dollar display also, right? Now and the next operators, before going to this concatenation operator, I'll discuss a few programming, okay, related to this. So with this example we can understand how we are using this conditional operators, right? Now see, in this statement, just I'll write a simple Verilog program to understand this. Now here this expression is unknown. Okay, this is unknown. The conditional expression is unknown. In that case, then it compare these two. Okay, 0 0 1, and these two expression it compare bit by bit. It compares 0 0. So both are same, then output is 0. If both are different, it returns 1. In this case 0 0. Okay, both are same, it returns that bit. In this case 1 1. So both are 1, then output is 0. So for this the result is 0 0 1. So that out equal to 0 0 1. Now we'll execute and we'll check once. Okay, now save and run. We'll execute this program once. We'll see this output. So the send so just I'll display this out. Okay, so now that out is here 0 0 1. Now here see the out equal to 0 0 1. So if the expression, the conditional expression is unknown, then it compare bit by bit of true and false expression. Now we'll check another, see, we'll check another assign statement. Now here in this case, so that expression is 1 tick by x. Here also the expression is unknown. Here also the expression is unknown. So just we'll compare these two. Okay, here one expression is 101, another one is 001. So 1 and 0, this 1 and 0. So here 1 and 0, both are different. Then it returns x. 0 and 0. Okay, this 0 and 0. Oh, here 0 only. 1 and 1. Okay, this one and this one, both are same, it returns 1. So in this case the output is x01. So we'll check once, right? So when run, we'll see what will be the output. Okay, in this assign statement, now check, we'll see, then output is out equal to x01. So now here the output equal to, here see, so now the output equal to here x01. I hope you understand how we are getting this x01. Okay, so now see another assign statement here. Now see this assign statement. So here assign out 3 tick by x 5 colon 3. Now here, so here the conditional expression is a 3 bit, that too all are x, all are unknown. Clear? All are unknown here. Now see here this 3x here. So what is the condition here? 5. 5, how do I represent the 5? Sir, 1 0 1. Okay, so now 3 means 0 1 1. So now it compare both. Okay, bit by bit, 1 and 0. So it return x, 0 and 1 x, and 1 1 x. Now we'll check. Okay, what will the output for this? Okay, just I hope you understand how we are getting. Okay, if that conditional expression is unknown, then it evaluate both true and false expression bit by bit, then we are getting xx1. So this is the output we are getting here. This is the output we got. Okay, here xx1. I hope you understood this. How can we use these conditional operators? Just check these two, right? See, I'll check one more assign statement. So let us check this final, okay, this one. So now here out equal to 3 tick p 1x0, okay, colon 5 colon 3 here, okay, 1x0 question mark 5 colon 3. So what will the output now? Tell me. Pause the video and try to find the output for this case, right? So now here, what will the output here? The output is 101. So now what will the output here? The output is here, the output is out equal to, in this case, then out value is 101. So why we get 101? Now see, what is the conditional expression here? 3 tick b 1x0, yes or no? So now tell me, irrespective of this position, either maybe 0 or 1. For example, x is equal to 0. In that case, what will the expression 110? For example, x equal to 1. What is the conditional expression? 100. Irrespective of this x value, what it is a true. Any non-zero value is a true. This is also true. Okay, this is also true. So in this case, this expression is always true irrespective of that bit position, like x, either maybe 0 or 1. So what is that? If it is true, what will execute? It returns only 5. Then in that case, out equal to 101. 101 nothing but only 5. So out is a 3-bit binary, yes or no? I'm just displaying in binary. So now that out equal to 101. I hope you understand, right? So irrespective of this x value, either 0 or 1, this conditional expression is true. Then it takes this true expression assigned to this out. So you should know these all conditions, how these ternary or conditional operators working. Okay. So without knowing, if you write, then you will get output maybe x or 0. We don't know how to evaluate this expression. Clear? Right. The next. I hope you understand how we are using a conditional operator. Now coming to the concatenation operators. So the concatenation operators, like wait a minute, concatenation operators provide a mechanism to append multiple operands. So if you want to concatenate 2 or more operands, we'll use this. Okay. So concatenation are expressed as operands with braces. So with commas separating the operands. If you want to concatenate 2 operands, those are separated by commas in these braces, right? Operands can be scalar net or maybe registers, or maybe vector net or vector registers, or bit select or maybe pod select, or maybe a sized constant. So now see some examples here. Now see in this example, I'll take one operand a 1 tick p1, size is 1 bit. Here b is another operand, size is a 2 bit, like 0 0. C is a 2 tick b 1 0. Another operand d is a 3 bit, 3 tick b 1 1 0. Now if I perform y equal to b comma c, so these are two operand concatenate as a single operand as a y. Okay, so braces b comma c. So what is the b? B is the 0 0. So now 0 0. What is the c? C is the 1 0 1 0. Now the result is 4 bit. By combining these b and c, the output is 0 0 1 0. Same way, if I concatenate a comma b comma c comma d, so what is the a value here? 1 bit. Here we'll get 1 bit. So b value is 0 0. We'll get 2 zeros here, and c value is 1 0. Now we'll get 1 0, and d value is 1 1 0. We're getting 1 1 0, and we are adding like 3 tick b 0 0. Okay, 3 bit value. So these are 0 0 1. I hope you understand. So how we are concatenating 2 or more operands as a single, right? So now here y a comma b of 0 c of 1. So like that also we can take, right? A is like 1 bit 1, b of 0 is 0, and c of 1 is like 1. So 1 0 1. So now we'll get y equal 1 comma a. So result y is 1 1. So what is the a? Y is the 1 bit. You may get doubt. So always we'll use like a sized constant. But in this expression, what is the 1? We didn't specify any size. So in that case, it will take that all unsized constant will be used as the 30-bit constant. 32-bit a constant. Now if you want to represent y equal to 1 comma a. So now you may think that, okay, right? So now it is, for example, 2-bit here. A is a 1 bit, and another one we are appending 1. For example, if I write y equal to, right, for example, I will give another example. For example, if I write y is equal to a comma 1. What is the output? Now tell me, what is the y value for this? So it is a 1. In case of 1, So now how do we represent this unsized constant? Will be used 32-bit constant. Okay, now it is a 32-bit constant. If I concatenate a comma 1, so what will the output now? So now for example, how do I represent? So now this is a 33-bit representation. Yes or no? This is the 33 tick B. So now how many? Here 1. So A is a 1. So remaining 32 bits are all zeros and 1. This is the actual uh, result of this one. So we'll check once. Okay, we'll see some program and we'll get an idea. Okay, I'll show program what will be the value of 1 comma a comma 1. Now see this program. Just I'll declare two variable a comma b as a reg type, 2 down to 0, 5 down to 0, initial a equal to b. So in this case, for example, if I write, okay, so first I'll take this, I'll execute b a comma 1. So now you are specifying the width. Okay, the width is 1 here. So yeah, if I execute this one, see the output. Just I'm displaying both a and b, right? Now see. So the answer, the a is 101. Anyway, the a is here, the a value is 101. Clear? In this case, what is the a? A is 5, nothing but 101 only. So what is the b here? B, write a comma 1 tick b 1, 1 tick b 1. So now what is the a value here? Okay, so b is 1. So a value, what is that? 101. So how many bits I use here? 5 bits. That is the reason I'll get, clear, 6 bits. So that is the reason I'll get this is my output. Now see this output. The b is 00101. Now I specify here it is a 1-bit constant. Clear? Now same way, for example, now in the same program, now here in this case, just I display a and b value. So I didn't specify in this program. I didn't specify. Clear? So I didn't specify the width. Just I'll use just b is equal to a comma 1. I'll use like this. So just I'll run this program. We'll see this output. This is the output. Now see here, that answer is 5 zeros and 1. So for this, what is the answer here? Now see this, what is the answer here we can get? The answer is here, see. So b is equal to 5 zeros and this is the 1. So why? Because this 1 is unsized constant that we can represent by using 32-bit. Yes or no? We require 32-bit, but the b is only 6-bit. So we represent only with the 6 bits. So now that a is 1 anyway. For example, a is here 5. Nothing but 101. So 101 and we require 32-bit like zeros up to 1. Okay, this is the actual b. The result is 32 plus this 3 bits. Clear? Like we get 38 bits. Okay, 32 plus 3, 35 bits we require. But we are using only 6-bit representation. So we are truncating into the only 6 bits. So the result is 00001 only. Okay, you won't get like 101 0 like that. You are getting only as a 1 as the output. We are truncating only 6 bits because this one required how many bits? 32 bits. Now see in this example, right? Now see here somewhere. Now see, unsized constant 1 is used in the concatenation. Okay, this 1 is used in the concatenation, will be used as a 32-bit constant. I hope you understand. So what is the difference here? Just here I'll represent the size in this expression. In this expression I didn't specify the size. In this case it treats as a 32-bit constant. I hope you understand this concatenation operators. So where in this case, now this one, okay, this unsized one is treated as a 32-bit constant, right? Now coming to the replication operator. So we can repeat the same number by using a replication constant. So replication constant specify how many times you want to replicate that number inside the braces. Now here this is the syntax. This n represent how many times you want to repeat this m in that, right? Now see some example here. 1 tick b 1, 3 b is equal to tick b 0 0, c is equal to tick b 1 0, 3 tick b 1 1 0. So just I'll declare like 4 variables. Now if I want to write y is equal to 4 braces a, what is the meaning here? Now I want to replicate this a 4 times. The result is 4 tick b 1 1. What is the a is the 1. So in this example, so 4 tick 4a comma 2b. So just I'm using both replication and concatenation operators. So now I want to repeat a 4 times and b 2 times. Now a is of 1 4 times. Now b is the 0, 2 times 0 0 will get. So same way like here 4 like braces 4 a 4 times and b 2 times and c. The result is like this. So now how many bits? Okay, here 4 bits, here 4 8 plus it like 10 bits total. So now 4 times a 1 1 1, b 2 times 0 0 0 0 and c is the 1 0. So now I hope you understand how to represent okay, how to find the result for a given expression in a Verilog. So operators are very useful. Not only finding the result of a given expression, you should have some practical sense where should use this operator, how to use these operators in program, and also you should know the precedence of operator. If that expression contain multiple operators, how to find the result of a given expression. Okay, so by this video I hope you understand Verilog operators, that means expressions with okay, I explained this suitable example. Please okay, pause the video wherever I'll show some example. Okay, try to find the expression of that result of that expression. I hope Verilog operators are cleared. Thank you very much.
Yeah.